some of the MATLAB point of view. They will be giving you an they will be introducing you to the MATLAB toolbox where you can actually solve all the optimization problems. And obviously, power system is huge, and it is not possible to solve all the problems by hand. So you need to use some toolbox or some mathematical tools to solve those big problems. So let us start our eighth lecture on optimization preliminaries, which will be basically an objective function, constraints. Then we discussed about the some of the methods to solve an optimization problem. And as I again am reminding you that this is the best method, interior point method, and it was actually developed by an Indian. The name of the mathematician was N. Karmarkar. So he actually developed this method, and this is by far, or till date, this is the best method to solve an optimization problem. Then we discussed about the classical technique where we just take the derivatives, one single derivative, and when we equate it equal to zero, then we get a solution which can either be local or global optima, or maybe a saddle point depending on the fx, the type of fx we have. Now, we also talked about equality constraint optimization problem, and I told that again you have to form a Lagrange function. This is actually known as Lagrange function. So, and this lambda here, it is a Lagrange, there are a lot of names for it. This is a Lagrange multiplier, or you can also call it as dual variable. This is also another name for it, dual variable, because primal variables are like, from a power system point of view, primal variables are like, we want to minimize the generation, we want to minimize or keep the voltage within a particular bound. So those are the main variables which we want to optimize. But these lambdas are basically auxiliary variables which appeared because of this formation of this Lagrange function. So that's why we call them dual variables. So here x will be actually a primal variable, and lambda will be a dual variable. We can also call lambda as a Lagrange multipliers, as I told you before. So you just, the logic is same. We take the derivative in terms of x and lambda, we equate them equal to zero. Yeah, graphical illustration today we will see once we solve a numerical example. It will be easier to visualize. And what I was saying in the last class, that the gradient of fx and gx must be collinear. From this formula we saw that that lambda will be equal to minus fx by gx. So this we will see why we are saying this we will see from the from a numerical problem. So, and then we saw that if we have an inequality constraints apart from just fx and gx, if let's say there is another equation which is of inequality type where hx is less than equal to 0, then how we solve it. And we discussed that this is actually developed by a KKT optimality condition. KKT is Karush-Cohen-Tucker conditions. And again you form a Lagrange function where you have mu hx additional term, and then you take the derivative in terms of x and lambda here, but for mu hx you add a complementary slackness condition. And with this condition, what we mean here, if let's say hx is equal, so mu hx is equal to 0, so either hx can be 0 or mu can be 0. So if let's say hx is 0, then mu can be any value greater than equal to 0 or not equal to 0. And if hx is less than 0, then mu will be equal to 0. So in any sense we can observe it. So we'll see again this type of in an example today. We'll be solving a numerical example to prove this, or to see how this method works. So let us solve a quick example. So please have your pen and paper with you, and you can solve this problem. So let's say if we have an objective function with which has two variables x1 and x2, so let's assume 0.25 x1 square plus x2 square, and subject to a equality equation where I'm calling it equality equation as omega, and this equality equation is 5 minus x1 minus x2 equal to 0. Now what will be the first step to solve this? How to solve this? So you will be telling me and I'll be solving it. So you have to tell me what will be the first step to solve this.
Lagrange function.
Perfect. So we have to form a Lagrange function. Can you help me out? What will be the value? Can you name form the Lagrange function for me? So L
Sir,
will
f x1 x2
yes.
plus lambda omega x1 x2.
Good. So as you can see here that L is this f plus lambda x1 x2 omega x1 x2, and then L, if you write in the mathematical sense, it will be 0.25 x1 square plus x2 square plus lambda 5 minus x1 minus x2. Right. Now what is the next step from this?
So to find dl by dx and dl by d lambda.
Good, good. So dl by dx means you have to take dl by here when we say d is not this d, it is actually the partial derivative. It is not the full derivative. So I hope you know the difference between both derivatives. So you can easily search and find it out what is the difference between. So we do take actually partial derivatives, and you have to take partial derivatives in terms of x1, in terms of x2, and then in terms of lambda. So can you tell me what will be the values if we take in terms of x1? And then we equate it equal to 0, or rather I can just show you. I have already done that, so you can do it on your own and tell me the values of x1, x2 and lambda. Anybody, what is the value of x1, x2 and lambda? Take the derivatives in terms of x1, x2 and lambda, equate the equations equal to 0, and then you can calculate the value of lambda x1, x2.
So x1 is 4, x2 is 1 and lambda is 2.
Okay, good. So if you take derivative in terms of Lagrange in terms of x1, this will be 0.5 x1 plus minus lambda. Yes, actually your answer is correct. So just wanted to for everyone. So when we take in terms of x2, it will be 2x2 minus lambda will be equal to 0, and lambda could be either 0.5 x1, lambda could be 2x2, and then you can equate this in the equality equation, and then you will find lambda is equal to 2, and x1 will be equal to 4, x2 equal to 1, and f will be equal to 5. Clear? So I hope everyone else also they are also getting the same answer. Now just to see what I said in the previous lecture, that the solution wherever will lie where the derivative of fx and derivative of gx are collinear. So what do we mean? It will lie, sorry, yeah, it will lie exactly on top of this line, right? So there will be no other solution. It will only lie on this line. So that's what I wanted to ask you from everyone, that the solution is going to lie on this line. There is no other solution here. And now, because we know that with x1 equal to 4, x2 equal to 1, we know the f value is 5, and wherever this f5 is intersecting with this line, there only the solution will be. So this is going to be our optimal solution, which is mentioned here. You got my point, how we decide in the plot. Now, coming to the collinearity of this solution, if we just go to the next slide, I have already plotted it. So here, if you'll see from the collinearity point of view, that the if I basically draw a tangent on this f at this point, let's say this point, so the tangent on this line will be like this, and the normal of this tangent is going to be the this for the fx, and gx tangent is going to be on the same line because it's a line, so the tangent will be the same this point, or let me just quickly draw it in different color. So the tangent of gx will be on this line, and the normal of it will be here, right? So whenever we you can see that because we have already seen the optimal solution actually lies here, so we know that this solution is not going to be valid, because obviously you can see why this is not valid, because both are not collinear. So just wanted to prove the collinearity in a reverse direction, that whenever it is collinear, then only we get an optimal solution. So this is one thing. If we take this, if we do the same thing here in the lower half of this curve, here also you will see that they are not collinear. They will only be collinear when we have an optimal solution, otherwise they will not be collinear. I hope this is clear to everyone. Can anybody just confirm that okay, yeah, it is clear?
I'm completely on that.
Sorry, there is a lot of background
I
noise.
didn't understand
Okay, good, good, good. Okay, yeah. So, yeah, so this is the logic of collinearity. Now let us go ahead and add a inequality constraint to it, and then see how KKT helps us in solving this type of problem. Now let us do that. Yeah, now it is working fine, probably because of this charger. It is not. Yeah, so as I was telling you before, that this will act as a mirror. So basically, solution should always lie in this direction, right? Now, because of this equality equation, we can also say that solution will only lie on this line, and that too till this point. It will not lie in this direction. So this is not a feasible region. Feasible region is always on the left hand side, and because it is an equality equation is there, so this will always lie on this line on the left hand side, right? So the solution is going to be on this line. So that is what I wanted to tell you here, and I hope you can easily visualize this. Now let us solve this problem and see how KKT conditions helps us in solving this problem. So let us see that, and you have to solve it. So the first step is, as always, as you have correctly mentioned, is that the formation of Lagrange function. So I'm going to form a Lagrange function. So I'm adding a term mu gx, and this is going to be my Lagrange function. Now if we take the KKT and KKT conditions, that means that taking the derivatives and the complementary slackness condition. So let me just write down that complementary slackness condition here. Now, can you tell me how, I have, as I have already told you before, can you guess what is the next step? How to solve this, especially this type, this equation, how to solve this? How to solve this problem? Any guesses here? How to solve this problem? Any guesses? Any random guess? I actually told on the previous class. I hope it was clear. So that means it was not clear in my previous class. Just give it a wild guess.
We
Yeah.
should we should solve mu from two values starting from 0.
Yes, yes, okay. And okay, so yeah, it's a nice try, nice try. Good, good, good. I like that. Okay.
What about if I do differentiation for all these equations for x1, then I equal it to 0, and the next step is to differentiate it respect to x2, and then equal it to 0.
No, we cannot actually differentiate any further here. Uh, the idea here is what actually the I actually do not remember everyone's name right now, but the first person who said that the idea here is basically we know that both to make this equation equal to 0, either mu can be equal to 0 or this x1 plus 0.2 x2 minus 3 can be equal to 0. Agreed? So what you have to do, basically there will be two cases and you will be solving both the cases. So the case 1 will be mu equal to 0. Oops. So one will be mu equal to 0 and the second will be x1, and then the other will be like g will be less than 0, and the another will be is going to be g will be equal to 0 and then mu will be greater than 0. Right? So basically you have to take both the conditions and solve. So with this condition you will get one value of f. With this condition you will get one value of, let's say I call them as f1 and f2. So whichever, because this problem is minimization type, so whichever condition you get f1 is, or whichever condition, whichever is minimum, f1, f2, that will be your answer. So can you quickly solve and tell me what is going to be the answer? Just take the first step where mu is equal to 0, and then sorry, yeah, whatever, you can take either mu equal to 0 first, or whichever. You can just solve both the cases and tell me the answer. What will be the value of x1, x2, lambda and mu, because now mu is also there? So anybody who has solved the first case where mu equal to 0 is assumed? So if you assume mu equal to 0, I think you get the same answer what we got earlier. X1 as 4, x2 as 1, and lambda as 2. Right? Because it becomes the same problem. Are you all getting the same answer?
Yes.
Okay, good. Now because at when you solve mu equal to 0, so is it a feasible answer or not? Because when you assumed mu equal to 0, let me just quickly change the color. So when you assume mu equal to 0, then g should be less than 0. So what you do, you put x1 as 4 and x2 as 1 and see if this is coming out to be less than 0. So let's say I put here 4 plus zero point 0.2 minus 3, which is equal to 1.2, and this should be less than equal to 0, but this is not. So this is basically, this solution or this f1 or the first case is a infeasible case. So this is not valid. This is infeasible. Are you all agreeing with me that this is an infeasible case? Because if we are assuming mu equal to 0, that means g has to be less than 0. And if you put the values of x1, x2 and lambda, what you got after putting mu equal to 0, then the g has to be less than 0. But here it is coming out to be 1.2, and which is not less than 0. So that means it is infeasible. Do you agree with me? Anyone? Okay, I'm assuming everyone is agreeing with me. Now let us do the other case, the second case, when you assume g equal to 0 and mu is going to be greater than 0, and then solve and tell me the values of x1, x2, lambda and mu, because now mu is greater than 0. So what is the value of x1, x2, lambda and mu? Anybody? Anybody who has solved that?
X1 2.5, X2
Just a second.
2.5.
X1 is 2.5, x2 is
2.5
okay, same. Okay, and lambda?
mu.
Acha, mu. Okay, mu. What is the value of lambda and mu?
Uh, 0.85 mu.
Sorry, lambda, your voice got broke. Anyone else? Anyone? Lambda and mu, what is the value? You have to be quick because when during the exams,
Sir,
huh?
mu equals to minus 4.68.
Minus, it has to be greater than 0. Okay, minus 4.68 and lambda?
Minus 6.9.
Acha, both you are getting 6.9. Okay, can anybody else also confirm? Or everybody is getting the same answer?
Lambda is 5.93 and mu is 4.68.
5.93 and 4.68. Yeah, it should be actually positive, and I kind of agree, 5.93. So, sorry?
My answer is this 5.93 and 5.68.
Okay, good. ठीक है, so this is not the right answer. It is going to be 4.68. So anyways, I have solved it. So whenever you have the inequality expressions where we want mu gx equal to 0, basically of this type, then what we do, this is a case, and you have to solve all these cases to get all the answers. So here, when we put this 4 plus zero point 0.2 minus 3, so this is becoming infeasible. So basically this is of no use because obviously this is infeasible, so we'll ignore this. And this is feasible, so this is the final answer. And here we are getting f as 7.81. So it is not always that it will, one of the case will be infeasible. It is just in this situation it is happening. But if, let's say, if both are feasible, then you will choose the solution, or the optimal solution will be that solution where you got the minimum function value. Okay, so I hope this is clear. So the whichever gives the minimum function value, that will be your optimal solution. Right, now let us see where does this point to the previous slide. It actually deletes everything, and that's the problem of PPT. I don't know how to resolve this. So again I have to draw. So let me just quickly draw it again to explain you that. So let's assume there will be one f here. So here it will be in this direction, here it will be in this direction, here both are going to be collinear, and here it is going to be like this. Okay, now what we do, because the resultant, if you see the resultant of this will be on top, this resultant will be in this direction. And if you see that lambda is minus partial f by partial g, so that means the resultant will be in reverse direction. So you have to take the resultant in this direction. So basically, if this lambda, value of lambda is huge, if the lambda value is very high, that means the force at which it is pushing the solution to arrive at an optimal solution where both delta f and delta g will be collinear is very high. The force is going to be very high. If the lambda is very small, that means the force is not very high, and lambda means, that means the solution is already somewhere close to this value. So you get the physical interpretation of it. It is like a force at which the updation will take place, or the collinearity achievement will take place. Do you get my point here? In a crude manner, it is just a force which brings the solution to an optimal point. Clear? Is it clear? Can you please confirm?
Yes, sir.
Okay, good. So obviously, if we have less number of equality constraints, if we have less number of inequality constraints, we can do all these hand calculation. We can visualize all these problems here. But as the problem grows, means if we have more number of equality equations, we have more number of inequality equations. It is extremely difficult to solve the problem by hand. Then we need some mathematical tool or some algorithm which will solve everything, will do all these things automatically. We do not have to do all these things manually. So for that, we are going to see in the next lecture how the iterative methods are there which can solve big problems in a very fast manner. Okay, so we are going to see that in the next lectures.